So hello guys, this is good evening everyone. I am Govind Arora as Journal Secretary of Open Pharmacy Federation. On behalf of Open Pharmacy Federation family, I welcome all the international webinars on immune response in COVID-19 for the spreading more awareness and safety in the case of coronavirus pandemic. So as you know that situation for everyone needs to improve their immunity and all, as the pandemic is all about getting your immunity back. So here we would be talking about the coronavirus, novel coronavirus that has spread quickly throughout the world. So COVID-19, as everybody knows, that spreads easily between people and it has a community contact spread over in all now. As it now in the world, there is no specific solutions to the and just rather than self-isolation. So today we will be talking about how our immunity systems could be strong, and we have experts which will be giving you overview about it. As we know that the topic for today is immune response and COVID-19. This unique theme is selected for spreading awareness about about building strong immunity power in novel coronavirus and to spread in the public and the students. As we today have a lot of students, a lot of academic people who are right now giving to it. Today we have one of the renowned immunologists from Malaysia. I would like to welcome Dr. Rajesh Ramansri from University of Putra, Malaysia, which will speak to us about the topic for the response of COVID-19. Now I would like to offer some introduction. I would request our director and founder for Vikram Chaudhary please to just put a light on it. Okay.
Yeah, good evening everyone. Dr. Rajesh Ramasamy is the currently Associate Professor at the University Putra, Malaysia and Advisory Board member of Operant Pharmacy Federation. He has earned his degree in Biomedical Sciences with a specific interest in immunology at the National University of Malaysia in 2000. In 2006, he gained PhD in stem cell transplantation immunology at Imperial College of London, UK, working with Professor Francisco Desi. In his PhD work, he pioneered the investigation of immunomodulations exerted by human mesenchymal stem cells on both normal and malignant immune cells as a tool for treating grafts versus host disease in the transplantation setting. After completion of his PhD, Dr. Rajesh Ramasamy joined the Faculty of Medicine and Health Sciences (UPM) as an academician cum principal investigator at Stem Cell Immunity Research Group. At the beginning of his career, he worked mainly in the understand the molecule and cellular mechanism of immunomodulations produced by various types of human mesenchymal stem cells and different immune cells. Besides his primary focus on the stem cell mediated immunomodulations, his research work is diversified into stem cells related research work in cardiovascular diseases, diabetes, cancer, aging, and medicinal plant research. While at UPM, Ramasamy continues his work in decoding the interaction between mesenchymal stem cells with various immune cells. The research outcomes of his stem cells immunity research group signaling the pathway in almost immune cells. He finding further encouraged in use of mesenchymal stem cells as an ideal tool for harnessing the unwanted immune response. In 2015, he pursued a sabbatical at King's College of London and Regenerative Medicine Unit, where he focused on the production of mesenchymal unit stem cells and unraveling the cellular crosstalk between the mesenchymal stem cells and leukematic tumor cells. He has served various committees at the university national and international levels. He is the one of the panel member of Grant Evolution Board at the several universities, Ministry of Energy, Science, Technology, Environment and Climatic Sciences. Served as the evaluator of Medical Research Council (MRC) UK. He is also the panelist of the National Ethics Committee for the Cell-Based Research Therapy (NSCERT) at the Ministry of Health Malaysia for the evaluating stem cells research and therapy. Dr. Ramasamy is the editor-in-chief at the Regenerative Research and International Journal that thumbed on the regenerative medicines and tissue engineering. Besides, he also served as the editor and coordinator of Malaysian Journal of Medicines and Health Sciences. He has graduated over 30 research-based postgraduate students and published over 19 publications in reputed journals. Now I request to Dr. Ramasamy to start today's webinar on immune response and COVID-19. Please, Dr. Rajesh Shamasa.
Thank you so much, and I would like to express my warm thank you to Mr. Vikram. Thank you so much, my pleasure as well.
Yes, sir.
Okay,
You may start, sir.
okay. Thank you so much, Vikram, for giving me this opportunity, and also the chairperson of today's seminar, and also the panelists, and all the researchers throughout the world, and the postgrad students. And today my talk will be the immune response and COVID-19. And I will be start my talk with introducing the immune system. And most probably not all of you are actually aware of the immune system. And then we will move towards the immunity towards the virus. And then at the third level, we will learn or discuss about that the immunity towards the COVID, the corona, that what you call SARS-CoV-2. So please bear with me for a stage by stage. So until we come to that immunity towards the COVID-19. And let's start our talk now. Um, okay. Okay, this is what the entire world, okay, actually having a great health challenge, which called as COVID-19. This COVID-19 is actually caused by the SARS-CoV-2, and I will come much detail on this later part. And before we get into our topic, let me to introduce what is the immune system. As you know that immune system is an army or policeman of the body. They protect us from invading or infecting pathogen. When I say pathogen, pathogen can be any harmful materials or more precisely microorganism. So we do have a virus as a pathogen, or that bacteria, or parasite, even the fungi. Okay, all these things are considered as a pathogen in immunity. And we have a two kind of immunity. The first one is innate immunity. The second one is adaptive immunity. In my presentation, if you think I'm talking too loud, too fast, or you need some extra time to assimilate certain facts, please let me know. Okay, so get back into immunity. The first one is innate immunity, or we call that as inherited or naturally occurring defense system. When a baby born, it comes with it equipped with that innate immunity. Innate immunity is not specific to a particular pathogen. This is a first-line body defense system, and it mainly consists with the granulocyte, monocyte, macrophage, and dendritic cell. When I say innate immunity, and the major point here is not specific to a particular pathogen. It means innate immunity does not use a single or specific antigen on the surface of that pathogen, okay, to recognize them as a pathogen. It simply means that, I'll give you an example. So we have a bacteria called as Staph aureus. The Staph aureus belongs to a bigger family of Staphylococcus. So innate immunity able to detect a general antigen on the surface of all the staphylococcus. Okay, it can detect the pattern of the antigen, or it can detect the general antigen on the surface of a group of microorganisms. Unlikely adaptive immunity, they have very specific immunity, whereby a specific antigen that belongs to Staphylococcus aureus species will be detected by the adaptive immunity. The specificity largely discriminate between the innate immunity and the adaptive immunity. Adaptive immunity is formed during infection. It's more like uh, when baby is born, when the baby encounter a new infection, the body start to produce the antibody and also start to produce other immune cells. Thus, we call adaptive immunity. It is specific to a particular pathogen. And more interestingly, the adaptive immunity will have the immunological memory. This is very important when it comes to vaccination. Why we have to vaccinate ourselves? To protect ourselves from a future infection. In order to us to be protected, the body should keep their immunological memory. The immunological memory only available from adaptive immunity, and the adaptive immunity is mainly driven by the T and B cell. Unlikely for innate immunity, we have a granulocyte. When I say granulocyte means a cell that has many granules. So in the leukocyte population, neutrophils, basophil, eosinophil are regarded as a granulocyte. And then we have a second category of cell called monocyte or macrophages or dendritic cell. These cells are very important because they are the inducer of the acute inflammation. At the same time, they are the messenger to the adaptive immunity. So we have roughly understand what is the innate immunity and adaptive immunity. And what you're going to see here is, let's say someone who has been infected with a particular bacteria, even viruses. So the innate immunity not only consists of the immune cell, it also consists of the structure of the body. Let's say in the case of the COVID-19, SARS-CoV-2 infections. SARS-CoV-2 infection are actually entered through our nasal area, and it reached the alveoli through the epithelial cell barrier. So the epithelial cell barrier is considered as a component of the innate immunity. In the innate immunity, we have multiple cell, phagocyte, a cell that perform phagocytosis called as a phagocyte. It could be monocyte, macrophage, even a neutrophil. Then we have a complement system, and also we have very precisely NK cell. Why I say precisely NK cell here is because later NK cell play a major role in the innate immunity of the virus infection. After a few hours of the infection, then the immune system actually drift to the adaptive immunity, whereby we have a B cell that potentially produce a specific antibody towards the infectious agent. It could be anything, a bacteria or viruses, or we have a T lymphocyte. T lymphocyte is very important in the adaptive immunity because without the T cell, we are unable to mount an effective B cell immunity or CD8 T cell immunity. When it comes to adaptive immunity, we have a two kind of immunity. One is humoral immunity, which was driven by the antibody production. The second one is cytotoxic or cellular immunity, whereby we have a killer T cell that kill potentially virus infected target cell or tumor transformed cell. So we need to know. So we have innate immunity and also adaptive immunity. When it comes to a viral infection, the NK cell from the innate immunity and CD8 cell from adaptive immunity play a major role. And virus infection. Virus is intracellular microorganism. It means virus require a living cell to sustain. The virus most probably can be in the outside for a few hours, but in order for them to replicate and spread the infection, they need to be in the living cell. So basically, virus is an intracellular microorganism, and they use host cell or target cell machinery to produce their own nucleic acid. It could be RNA or DNA, and also produce their protein synthetic machinery. Okay, so viruses are intracellular microorganisms. They exploit the whole cell machinery to produce their own nucleic acid. It could be RNA or DNA, and also protein required by the virus. And often, virus viral replication interfere with the normal function of the protein synthesis and also the physiology of the virus, which eventually lead to the cell death of the infected cell. And most importantly, virus enter host cell through receptor binding on the surface of the cell. So a virus can simply, like a HIV virus, use CD4 cell as a gate, as a portal to enter into a T cell. Likely, SARS-CoV-2 actually use ACE2 receptor to enter into the cell. So virus require a particular specific receptor that uptake the virus into the cell. And and you may want to think, okay, our body and also all the cells and immune cell actually equipped with the senses. whenever there is an infection in the body, in the cell, or even the outside the cell, the body, the immune system able to sense the infection. So the sensing of the infection is actually different between the innate immunity and the adaptive immunity. In the case of innate immunity, which is the host cells and also the other neutrophil, macrophage, and monocyte, they do have a specific receptor which we call pattern recognition receptor. Here you have to focus here. Why this is called as a pattern recognition receptor? So as I said earlier, innate immune cell is not licensed to identify a specific receptor that specific for that a particular species, a particular microorganism. They only able to detect a general pattern on the group of the microorganism. So since they are detecting a common pattern that's found on a group of the microorganism, we call this as a pattern recognition receptor, or we call PRR. So PRR expressed in most of the innate immune cell and also epithelial cell. Remember, epithelial cell as well, components of the innate immunity. Although it is not innate immune cell, but it is a component of the innate immunity. And now, let's see talk about the immunity towards the virus. So we have a two innate and adaptive. And usually, when it comes to a virus, the two kind of that the protection needed. One, to block or to prevent the virus from entering into the cell. Because viruses are intracellular, they require living cell to produce their nucleic acid and also protein. So they has to infect those cell. They have to enter into the cell. So if we can prevent that adherence and that entrance of the virus into the host cell, we can stop the infectivity. Other one is once the virus infected to the host cell, so we should able to release the virus from the host cell in order to kill the virus. So there are two things of the protection. One is first layer, which is the blocking of the infection from preventing the virus enter into the host cell. Second one is upon entering into the host cell, we should able to release the host cell or kill the host cell to release the virus so the virus can be neutralized by the other immunity. So when it comes to a viral immunity, there are two major cells. One is NK cell, other one is CD8 cell. Okay, NK cell belongs to innate immune cell and CD8 cell belongs to adaptive immune cell. Injection is prevented by, in the case of the innate immunity, type 1 interference is a part of innate immunity and neutralizing antibody that contributed by the adaptive immunity. So as I said, first prevention by preventing the uh, entrance of the cell. Second one is killing the virus infected cell to release the virus to eliminate the virus. So the through that innate immunity and adaptive immunity, innate immunity actually produce the type 1 interferon and which prevent that spreading of the virus. And when it comes to adaptive immunity, the B cell can produce an array of the different kind of the antibody that block a bind with the virus, so the virus unable to bind to the receptor which found in the target cell. So once the infection is established, okay, in the case of COVID-19, we don't have any immunity because we never encountered this virus previously, so we don't have antibody. So in the case of COVID-19, the virus easily can enter into the cell because there is no immunity, there is no antibody. So once the cell enter into that into the target cell, NK cell from immune system and also CPL, cytotoxic T lymphocyte, able to kill the target cell, release the virus, and the virus later been cleared by the other immune system. Okay, so that's what you're going to see here. One is innate immunity, adaptive immunity. Innate immunity produce a type 1 interferon which prevent the spreading the virus, and we have an NK cell. NK cell kill the virus, kill the infected cell through kill is a way of eliminating virus. In the adaptive immunity, we have B cell produce the antibody which neutralize the virus, and we have CTL or cytotoxic T lymphocyte that potentially kill virus infected cell. The virus will be released and subject for a neutralization. And this is a very specific on the innate immune response. The principal mechanism of innate immunity against virus are inhibition of the infection by type 1 NK cell, and virus infected cell produce type 1 interferon. You may want to know what is a type 1 interferon. Type 1 interferon is a specific cytokine produced by virus infected cell as an autocrine control system and also paracrine control system. The type 1 interferon will prevent the virus replication. And as you know that, and when as what we all know, when a cell infected by the virus, the MHSC1 expression of the infected cell reduces. All of us know that all the cell with the nucleus, they express MHSC class 1 except the red blood cell. MHSC class 1 is like a passport, a visa for every cell. Every cells of our body will express MHSC class 1. And MHSC class 1 required by the T cell in order to recognize the antigen. So, in the case of virus infection, viruses are very clever. They always try to encounter the body mechanism, the body's defense system. So one of the way virus escape immunity is to reduce the MHSC class 1 on the target, on the virus infected cell. However, so because of reduced MHSC class 1, the particular cell may be escape from CTL. However, NK cell NK cell has a specific ability whereby NK cell can sense the reduction of the MHSC class 1 expression on the virus infected cell. So let's say if a cell expresses about 500 molecules of the MHSC, in the case of the virus infection, most probably the cell only will express 50 MHSC. So the NK cell able to recognize the difference or the decline in the MHSC class 1 expression, and they kill the target cell by producing two type of that biomolecules called perforins and granzyme. Okay, that's by the innate immune system. When it's come to the adaptive immune system, we have that antibody produced by B cell which blocks virus binding and entry, and we have the cytotoxic T lymphocyte or CTL that eliminate the infection by killing the infected cell. Antibodies are very effective against virus only during the extracellular stage. Okay, remember that antibody don't have an access to get into the cell. So when the virus are intracellular, when the virus are inside the cell, antibody unable to neutralize the virus. So the protection governed or the protection produced by the antibody is very limited. It is very limited when the virus are outside. And you should know when the virus are outside. The virus are outside when they are actually entered body and start to infect the cell, or when the virus copy in the target cell reach a maximum number. Now is a time for the virus to spread. So the virus will release the virus in the target cell. Okay, it will assemble the new virions virus and it will release into the environments. That's we call virus budding. And so in these two circumstances, these viruses are subject for antibody-mediated immune response. Okay, and also when CD8 cell or NK cell recognize the cell with the infected with the virus, they able to kill the cell, okay, in order to induce cellular immunity. The infected cell should sacrifice itself, okay, to be killed by NK cell and the T cell in order to release the virus. So when the virus are released to the environment due to cytotoxicity, the antibody surround the area able to neutralize the virus. Okay, so the antibody of virus require, the antibody against the virus required to neutralize them. What is the neutralize? So when antibody binds to the virus unable to attach to the host cell. So they are unable to infect or enter into the cell. The second thing is they will opsonize the virus or viral particle. What is opsonization? Okay, it's more like a burger. No, so if I give you a burger with the bread, did you eat? You don't eat, right? Because you're going to eat just simple bread. So you will add sauce, you will add meat, you will add mayonnaise. So you make the burger more edible, right? So opsonization is similar. Okay, when the virus bind with the antibody, now the combination of the virus and the antibody are more appealing towards the phagocyte. The phagocyte now can happily engulf that virus and antibody combination and clear them. The third one is by fixing complements and lyse the viruses. So the antibody mediated immunity, which is humoral immunity, it will block the infection and reduce the spreading of the virus from the cell to cell. But once the virus enters the cell, begin to replicate intracellularly, they inaccessible to the antibody. Means the antibody can't do anything. So now you need a second layer of virus immunity, okay, which is mediated by CTL, cytotoxic T lymphocyte. So cytotoxic T lymphocyte, okay, the function is the physiological function of CTL is surveillance against virus infections. Okay, so we have CD8 cell. CD8 cell very important in two things. One is to virus immunity, other one is the immunity. So here we will more focus on virus immunity. Unlike the NK cell can recognize any antigens on the surface of the target cell without any priming or activation. Okay, they are ready go cell, but T cell are very partial. Why I'm saying T cell is very partial? T cell need to be activated. So who will activate T cell? In our body, we have a specific kind of cell called antigen presenting cell. These antigen presenting cells basically mainly are dendritic cells and also monocyte and macrophage. So these cells able to take up the antigen from the virus and present the antigen to the CD8 T cell through MHC1 molecule. So these cells are very unique because they recognize the antigen from the virus in association with the MHC class 1. Okay, so once CD8 cell activated, they transform into effector cell. It means a cell that performs an immune response. So you need to understand in the real situation, let's say in the case of infection in the lung. So let's say lung infected by COVID-19, right? So the T cell wouldn't be there. Okay, so the antigen presenting cell which doing the routine surveillance, routine migration to every part of the body and look for a potential insult or potential microbe, they uptake the virus or the virus proteins or the virus protein that is released due to inflammation, and they uptake the protein and they will migrate to lymph nodes. In the lymph nodes, we have all the virgin, or we call all the naive T cell. So in the lymph nodes, we have a B cell, we have CD4 cell, we have CD8 cell. So the antigen presenting cell potentially present the antigen to CD8 cell and CD4 cell. So the CD8 cell now get activated, so they become an armor. They become an what we call sentinels of the immune system. So once they've been activated, they have to migrate from lymph nodes to the place where the infection is occurred. So they will migrate to the lung. In the lung, they will found that cell that express the virus antigen with the MHC class 1 as well. Okay, they know that all the cell express MHC class 1. In the MHC class 1, it has a small group. In the group, all the self-antigen and also all the antigen from infection will be presented. So the T cell able to recognize that MHC class 1 and also with the virus antigen, and now they able to kill the virus infected cell. And how it kills? It's very simple. The killing mechanism for T cell and also for NK cell is similar. CTL, they use CTL and NK cell produce three kind of that biomolecule or enzyme. The first one is perforins, granzyme, and granulosin. Okay, so you see this here. Okay, we have a target cell, and this LF1 and ICAM is addition molecule. Okay, so we have a CD8 cell. In the CD8 cell, we have all the granules. Okay, the granules to be released to kill that target cell. So the granule released into the immune synapse, okay, between the target cell and the CD8 cell or even NK cell. In the case of NK cell, you don't have this TCR. So in the granule, you have perforins, enzyme, and granulosin. So in order to induce apoptosis, okay, first the perforins from the granule will make a hole inside the target cell. So through the hole being formed, the granzyme will enter into the target cell through the hole made by the perforins to induce the apoptosis through caspase activation. Okay, so granzyme actually induce the apoptosis. Perforin make hole on the surface of the target cell in order to granzyme enter, and we have a granulysin. The granulysin is very important. Why? Because the granulysins and one of that molecule that blast lyse the cell. Only the cell lysed, the content of the cell, including the virus, will be released to the outer environments, and all other antibodies or complements are in that vicinity able to neutralize the virus. Okay, that's all about the basic mechanism, the basic immunity regarding the virus infection. Now we get into the COVID-19 and immune response. Okay, it's almost similar. And COVID-19 is caused by SARS-CoV-2. And importantly is why it's so dangerous and why the entire world is so afraid of COVID-19, because we never been exposed to that COVID-19. So we have no idea what will be the immune response against SARS-CoV-2. Okay, means we don't have any herd immunity. Let's say we have vaccination from polio and we have vaccination towards the rubella. So whenever we encounter these viruses, the body already have a memory cell or the antibody to prevent us to get the infection. But in the case of the COVID-19, we never have all these equipment. So, and also please remember, there is no conclusive data on the immune response against SARS-CoV-2, yet the immune response against this new strain virus are actually predicted or similar to SARS-CoV. So in the world, we have 3 times the epidemic of SARS, okay? The SARS-CoV, first time and second time, and also we have Middle Eastern, the MERS-CoV. So if we compare the SARS-CoV and MERS-CoV, the SARS-CoV actually resemble 80% of the SARS-CoV-2 and 50% of the MERS-CoV-2. So all our understanding of the immune response are actually based on our previous experience with the SARS-CoV and also MERS-CoV. eh? And also please remember that not all people exposed to SARS-CoV are developing severe respiratory illness. Only about 20% of the patients who had the SARS-CoV are actually prone to that severe disease. And let's we talk about the SARS-CoV in terms of immunological point. SARS-CoV infection can be roughly divided into three stages. The first one is asymptomatic incubation period with or without detectable level of virus. Okay, these are very critical stage where people don't have that symptom. People don't show there is a virus infection through any kind of the detection. So these people are freely roaming around. That's why MCO, the movement control order, been implemented to prevent the COVID spread due to stage one. The second one is stage two. Okay, and people who had a stage one, they will lead to stage two, where non-severe symptomatic period with the presence of the virus means the patient will show that symptom of that lung infection, and their test will show existence of the virus. And most of the patients, almost 80 to 85 patients, are actually stopped at the stage 2. Only a small number of vulnerable patients are actually linked to stage 3, which we call severe respiratory symptomatic stage with a high load. These stage 3 patients are very critical and they are high risk of the mortality. Okay, and the most common symptom of COVID-19, the symptoms are fever, fatigue, and respiratory symptoms means difficult to breathe. And severely affected patients develop the lymphopenia and pneumonia. Okay, the pneumonia actually we call as severe acute respiratory syndrome. And if you see that SARS-CoV-2, the novel coronavirus induced pneumonia, which named as coronavirus disease 2019, COVID-19, by the WHO on February 11th, the International Virus Classification Commission have given the name as a SARS-CoV-2. And coronavirus, as I say earlier, they have caused several epidemics. Okay, the first one, the earlier one is SARS-CoV-2 twice epidemic occurs. And we also have that other version which called Middle East Respiratory Syndrome MERS-CoV-2. And coronavirus are envelope virus. You see the envelope virus with the positive and single stranded RNA. Okay, the genome or the nucleic acid of that SARS-CoV-2 is RNA. The RNA is a single stranded. They do have the spike glycoproteins, right? And as I said earlier, viruses cannot simply enter into cell. They require a portal. They require a gate to enter into the cell. So they require a receptor to bind in order to get into the host cell. In the case of that SARS-CoV-2, the ACE2 is angiotensin converting enzyme receptor 2. Okay, so the SARS-CoV-2 bind with the spike glucoprotein, the spike protein of that SARS-CoV-2 bind ACE2 receptor on that host cell and enter into the target cell. And you need to know which cell actually contain the ACE2. In the human, the major the type 2 alveolar cell express SAR2. That's why the lungs being affected. Beside the lungs, also some portion of the intestine cell, and also kidney cell having that H2. In the recent study, people have shown that they do detect the SARS-CoV-2 in the urine and also that fecal sample of the patient, because both the kidney and the intestine cell actually have the receptor that able to detect the SARS-CoV-2. And the immune response induced by SARS-CoV-2 infection can be clinically divided or classified in two phases. The first phase is a conventional phase. Okay, whoever infected with the SARS-CoV-2, they will subject to phase one. It's the incubation phase and non-severe symptomatic phase. The second one is very most critical and also our concern, which is severe respiratory symptomatic stage. So in the phase one, what happened is The specific adaptive immune response required to eliminate the virus and prevent the disease progression to a severe stage means the body have to produce that antibody by the B cell. And as I say that the receptor for SARS-CoV-2 is ACE2 is mainly expressed by small subset of the type 2 alveolar cells. And as you know that once the SARS-CoV-2 enter into that alveolar cell, in the alveolar cell, we have the receptor called PRR. First of all, the SARS-CoV-2 should enter into alveolar cell through ACE2. Once they enter into the cell, in the inside, in the cytoplasm of the alveolar cell or target cell, we have endoplasmic PRR or we have the intracellular PRR. What is a PRR? PRR is a pattern recognition receptor. This is a common term to indicating any receptor of the innate immunity that recognize the pathogen using common antigen. So, as we know that SARS-CoV-2 is single-strand RNA. So once SARS-CoV-2 enter into the body, it will release the single-strand RNA. In our body, we do have inside the alveolar cell, and also other cell, we have this PRR, which specifically detect the single-strand RNA. This called as the TLR7 and TLR8. TLR means toll-like receptor 7 and toll-like receptor 8. And also we do have a RNA sensor. So these three, the engagement of the single-strand RNA by the SARS-CoV-2 with the PRR, which is more specifically TLR7 and TLR8, will produce some signal. The engagement of the virus material with the pattern recognition receptor, it produces some kind of downstream signaling cascade through NF-kappa beta to produce type 1 interferon. What's the function of the interferon? The function of the interferon is to protect the cell. Okay, the cell will produce the interferon, type 1 interferon. It could be alpha and beta, and this interferon can act autocrine, means through their own cell, and will prevent that replication of the virus through the multiple pathway. In same time, the interferon produced by the target cell or the cell which has been infected with the virus can help the cell adjacent to this, the neighboring cell, to give them information there is the infection of a SARS-CoV-2, and it will make the adjacent cell more resistant towards the COVID-2. So interferon type 1 is very important, a crucial first line body defense or innate immunity defense system towards the towards the SARS-CoV-2. And then we do have a Th1 cell, which is CD4 cell, and we have CD8 cell. Okay, CD4 cell require the help of the CD4 cell to become a CTL, and we do have a B cell. This immune response happen in the lymph nodes of our body. So the CD8 cell transform into a CTL, and B cells start to produce the antibody. And so the NK cell, okay, through the innate immunity, and the CTL through the adaptive immunity, they able to detect the virus infected cell. They lyse the cell. It will release the viruses. When the viruses are released, the antibody from B cell able to neutralize the virus. This is supposed to be happen. Okay. However, remember, viruses are very clever microorganism. Okay. It means it's very clever, it's very smart. It always have the way to evade or escape from immune system, especially with the interferon type 1. So the body, so since the virus inside the target cell, it will manipulate the system of the target cell not to respond to the type 1 interferon. So when this happens, okay, the ding dong between the immune cell in the target cell in the virus, and when the body unable to curb the virus, or the body don't have sufficient innate immune system, and also the relevant adaptive immune system, it will lead to phase 2 clinical stage, whereby the damaged cells induce innate inflammation in the lungs that largely mediated by pro-inflammatory macrophage and granulocyte. It means, since the virus are not being cleared by that immune system, so the body, the immune, the body will continuously send signals to their immune system. So the more macrophages and neutrophil actually recruited in the region of the inflammation, which is the alveolar tissue in the lungs, and they start to produce more pro-inflammatory macrophages. Okay, pro-inflammatory macrophages will exaggerate the inflammation in the lungs. So it will be a very toxic to the cell, kill most cells in the lungs in order to potentially to remove the virus, but it create a very severe lung inflammation which could be life threatening. So this entire situation where the macrophage and granulocyte produce an array of huge amount of the cytokine called as a cytokine storm. And in this stage, the phase 2, people usually, and what we could see is we will see the higher number of neutrophils in the blood, however very reduced number of lymphocytes. So what we could see here is those cells that produce pro-inflammatory cytokine are actually raised in the blood, and those cells clear the infection reduced in the cell, which is what we call create a very risky and danger environments for that patient. So in the cytokine storm, you will see interleukin 6, all these pro-inflammatory cytokine, interleukin 6, interleukin 8, interleukin 1 beta, and most importantly, we will also see granulocyte macrophage colony stimulating factor. This GM-CSF is a factor that induced to tell the bone marrow to produce more neutrophil and macrophages. And same time, it's also produce so much of reactive oxygen species, free radicals with the other chemokines to attract more innate immune cell. It makes the entire environment is very toxic, very severely inflamed, overly activated, which induce a lung inflammation, and later it lead to multi-organ failure. In the worst case, it brought the mortality of the patient. So this is what you got. This slide is just telling you what really what anticipated. So I say this. Why I say anticipated? We don't have very conclusive data on immune response towards the SARS-CoV-2. All our what we call anticipation and my explanation are based on the previous SARS-CoV and MERS-CoV. So it could be what we call possible that besides ACE2 receptor, CoV as well can utilize some other receptor to enter the cell. So, but we don't know yet. But this is just summary. Okay, we have the alveolar cell. Okay, in the alveolar cell, the virus enter into the cell through ACE2. Okay, the alveolar cell will produce type 1 interference. The type 1 interference will prevent the replication of the virus. However, when the body fails to curb the virus, what happens is it will produce an inflammatory signal where more macrophages and also neutrophils are gathered or accumulated in that lung site, where it induces pneumonia and lead to a cytokine storm, then multi-organ failure, and later, if not controlled, the mortality of the patient. In other end, we also have that adaptive immune system, the B cell, which produce antibody that neutralize the viruses, and it provide a better way to eliminate the virus. And we also have the Th1 cell, okay, Th1 cell, which help in producing CPL. So this is what you will see in that what you call SARS-CoV-2. and these results are based on that available literature, available scientific report. And I also want to reiterate this maybe will change slightly, even completely later, with having more result churn out nowadays. So with and now and today, I just wanted to I just saw in the WHO website. So now the entire economy is actually slowing down, and no one can do work. And now people asking whether can we have some sort of that what do you call what do you call some sort of what do you call measurement to say someone is free from COVID-19. This we call immunity passport or risk-free certificate. This will enable the individual to travel or return work assuming as they are protected against the reinfection. This usually happen when, as I say, that 80% of the patient of the COVID-19, they only up to phase one, which is stage one and stage two. They recover themselves because of the immune system, and they think that because they have developed that antibody, so they think they will not have a reinfection. However, today WHO in their webpage, if you could see that webpage, and what they say is most of the studies which we have now shows that people who have recovered from infection have antibodies to the virus. However, some of these people have very low level of neutralizing antibodies in their blood, suggesting that cellular immunity may be also critical for recovery. So it is no enough sufficient evidence about the effectiveness of the antibody-mediated immunity to guarantee the accuracy of immunity passport or risk-free certificate. Means that when people have an antibody against SARS-CoV-2, it doesn't mean that they will be free from the reinfection in future. They may also have the risk for reinfection. So we cannot use this and the existence of the antibody as the assurance that you will be free from COVID-19 in future. So, and these are my reference. With that, I end my talk, and I will be much happy happy to what you call happy to have happy to participate in any sort of Q&A and forum. Please remember that this is just an open discussion. I have discussed, I have presented what people have reported until now. There are so many things need to be done. So the information which I shared could be null and void later in 6 months or 1 year, because there are a lot of studies are going on. So I'll be much happy and to take any questions. And I'm also much happy to learn from participants, because we may have virologists, we may have clinicians here who can equip with the better knowledge and information. So I thank you, Vikram, for the opportunity. So um, I ended my talk.
Thank you very much for your valuable presentation on immune response and COVID-19. Now this session is open for the question answer section. Anyone can self-mute and ask the questions.
First of all, very good evening, Vikram, Govind, and Dr. Ramesh. Dr. Gurjeet here. Hello.
Yes, yes,
Hello.
yes.
Yes,
We
sir. Yes, sir.
hearing you.
Yeah. First of all, I want to congratulate Vikram and Govind for and from the OPF to organizing this valuable webinar in current scenario of pandemic. Hoping you will be doing this in future too. And thanks for sharing your knowledge, Dr. Ramesh, on COVID-19 and immunological aspects related to COVID, and with respect to immunity and pathology. I just want to know about the plasma therapy. These days, there is a lot of shows on plasma therapy is effective in COVID-19 infection.
Oh.
What's your view on plasma therapy?
See, plasma therapy. See, basically, why we do plasma therapy? You want to replace the plasma with because usually people do. Uh, in my knowledge, in the event of cytokine storm, the body, the blood, the plasma are actually congested with many pro-inflammatory cytokine. So because of this pro-inflammatory cytokine surge is too high, which cause multi-organ failure. So the plasma therapy is one of the way most probably to reduce the pro-inflammatory cytokine. So the mortality rate of the patient will be reduced. It's just what you call you actually filtering out that how do you say that very innoxious substance from the blood. But please remember that it also may have some complication when you are actually introducing a third-party plasma, although there is no rejection because there is no cell involved, but also there is a high risk of transfusing some that proteins or molecules that potentially induce some immune consequences. But basically, the plasma therapy is just to reduce that pro-inflammatory cytokine that found in the patient's blood, so the mortality rate will be reduced. That's what I could think from immunological perspective.
Okay, thank you, Dr. Ramesh.
Hello, can you hear me?
Who's this?
I'm Anand Singhal, sir.
Yeah, Anand. Yes, Anand.
Yes, my question is that can homeopathic medicine help for COVID-19? So I have got one news that Zincum marticum 200 C tablets have been used for COVID-19 treatment.
See, I don't know how the homeopathic works, but remember, there is a different kind of immune response involved in that COVID-19, the phase one and phase two. And many people are thinking that immune boosting will be the answer for the COVID-19. But you see, the phase one require it may benefit from immune boosting because you boost your immune response, you boost your immune cell or your immune system to respond well to the infection. But in a phase two is due to an overly activated immune system, inflammation. In that circumstances, what you need is immunosuppression. That's why in China, recently there is one published paper, they have used mesenchymal stem cell to reduce the inflammation in the phase two patient. Okay, this is what I could understand. But your question is homeopathic, but I'm not a right person to answer that. I'm sorry, but I'm sorry. I don't know how to answer because I'm not the right expert to answer that. And plus, I have no idea uh, what sort of that medicines or the compound that homeopathy use to treat the patient. So I'm not the right person to answer that. I'm very sorry for that.
Okay, thank you, sir.
But remember,
Can I speak, sir?
because I want to reiterate this thing to everyone. The immune system, not boosting immune system, not necessarily good for the COVID-19 patient. The stage one, stage two, which is a phase one patient, they able to cure, recover themselves even without any treatment because their own immune system helping them. So in that time point, immune boosting most probably will work. But in the phase three, which is phase two, which is a stage three, which is a very detrimental, very critical stage, is due to over-inflammation. In that situation, you cannot boost the immune system. Boosting the immune system in phase two is detrimental. In order to reduce the immune system, but you are actually boosting, which is not going to be helped. So in the phase two, what you need is immunosuppression. That's why many people are actually doing that the stem cell therapy using not many people. There's one study, and there are several clinical trials as well going on to giving that mesenchymal stem cell as to suppress that immunoactivity, and even the plasma therapy. Plasma therapy as well is a kind of a therapy to reduce the pro-inflammatory cytokine. So phase two patient need immunomodulation, need immunosuppression.
Can I speak, sir?
Sure, please.
I'm a Professor Raju from Hyderabad, India.
Hi, Prof. Raju.
Very congratulating you, sir, for your good information regarding COVID and immuno response. I heard I read in fact one article regarding BCG is helping in how it is helping in immune response in the phase 1. Is there any
Um,
relation between BCG and these onset of infection?
BCG usually is come with adjuvants, right? So because what they have, what because I mean I try to answer based on my understanding. BCG usually come with the adjuvants, and most of the vaccines works well because the adjuvant in that vaccination formulation actually will enhance the immunogenic property of that antigen. So what we could do is the BCG adjuvants could be useful to how they say to boost the immune response, to boost the antibody production towards that towards the virus protein. This is based on my understanding, but but if you have any extra input, please feel free to share. Based on my understanding, is about BCG with the BCG which incorporate with the adjuvant will increase the immunogenicity of that antigen. That could be the way. That's what I could understand based on my understanding on that vaccination. And also, when it's come to vaccination, there is a many way of the vaccination. For instance, people are also trying to develop a bystander immune response as a vaccination. Bystander means there is an infection, but the body unable to produce the immune response toward the infection, but they may to inject something, they may introduce some sort of the compound, some sort of the cell to produce similar cytotoxic effect. So the cytotoxic effect produced towards the introduced compound can be used also to eliminate the virus. This we call bystander effect. People are thinking and evaluating the bystander effect towards to be used as a vaccination, and some extent people are using that the RNAs as source for that vaccination. But remember, vaccination is not an easy process. It requires many years. Okay, and also it's a multi-million-dollar because based on the vaccine developed through the FDA. So what they have roughly mentioned is vaccination may take about 10 to 12 years. It may take 500 millions to 1 billion. So at the moment, so it has a lot of what you call bottlenecks because from the finding the right antigen to induce the immune response. And also remember, vaccination trials are not on that patient. Vaccination trial on healthy control. So the safety issue of the vaccination is more stringent when it comes to vaccination. So again, back to your question, BCG, for my understanding, maybe the adjuvant actually can enhance the immune response toward the virus antigen or the virus particles. That would be with my limited knowledge on this part. Thank you, Prof. Raju.
Thank you, sir. Thank you very much.
Anyone more available for question answer session? Anyone can ask the questions from Dr. Rajesh Ramasamy.
We also have other panelists. Other panelists also can answer. Even the other participants, which they may more relevant to COVID-19, they also can share their knowledge. See, I'm good at the point of immunology, but they may have some other people who is good in the clinical management, good in other things. COVID-19 also can provide their inputs.
I have a question from Dr. Rajesh. Can you hear me?
I can hear you.
Okay. This is Vahid. Thank you very much for your presentation.
Vahid.
I would like to know, as long as the recovered patient from COVID-19, they contain the memory immune cells, why they might be infected again by COVID-19?
Okay, this is what I said in my last part of the talk. Because the virus immunity, okay, not only about the antibody. So how do we know that? Because see what WHO saying is people with the antibody towards the SARS-CoV-2, they could be free from that reinfection. But remember, the antibody, remember the amount of the antibody and also the efficiency of the antibody is very important. And not always that we will produce an apt antibody for that infection. And also, in come to a virus infection, you need a cellular immunity very importantly. So it can, because until now we don't have what you call evidence, okay, evidence from any kind of that published paper to saying that having the antibody will ascertain you to ensure you or to prevent for reinfection. We don't have any information, although you could be protected, but how extent we have no idea. So we can't say that. That's one of that one of that decision making point, saying that having the antibody will protect you from the infection, because we don't have any data yet, and we also have no data on how protective this antibody. Until unless a study been conducted several months and year, then only we will have the information. So at the moment, to think that having antibody in your body against SARS-CoV-2 will prevent you from reinfection is not fully true, because we don't have the data.
Thank you very
By
much,
basic
Ajit.
immunology, we may think, okay, because see, all our immunological knowledge are based on the previous infection, but in this infection, we don't have very concrete current data to make a solid decisions or solid conclusion.
This is Govind this side, sir. Again, hello,
Hello, yes.
hello. Yeah, so
Hello.
this is
Yeah,
Govind
I
this
can hear.
side again, sir. So,
Uh-huh.
so just wanted to know your view against the second wave and the herd immunity in this case.
Because herd immunity not been reached here, because see, because a community, because like any other virus infection, we have a vaccination and we have a natural infection with that induced immunity and antibody, the immunological memory within the individual. But in this case, we have no idea. That's why the entire world is very afraid and think this as a great challenge, because there is no herd immunity for this case. And what was the other portion of your question?
So what do you think about the second wave of this virus? It could be more impactful or
The
more
second,
strong than the first one.
we don't know, because it's all our fear. Because see, the world actually being preparing, the WHO is being preparing for if there is a second wave. We have no idea. Remember, those who are recovered from COVID-19, where they don't have the virus being detected, could be the virus are actually dormant. No, the latency period of virus could be long. Maybe the virus are actually hibernate. It's more like a human herpes virus, human simplex virus, HPV. Okay, those viruses are actually stay in the body. Whenever the immune response is down, it appear and cause that what you call infection. So this could be a case for SARS-CoV-2. We have no idea. That's why the entire world, the health professions, WHO, clinicians are actually making a possible way to what you call to treat, to handle, to manage the pandemic with the many other what you call corners. It could be okay. Those patients who have recovered from the COVID-2, maybe they will maybe who knows, they may have reinfection when their immune system is down. No idea. Hope it doesn't happen, but I'm just giving you an example, because we don't know. As I explained to you, we don't have any concrete data on this. All our all our discussion, all our action are based on the predictions from previous SARS-CoV and MERS-CoV infections. So it could be or could be not. I have no idea. But what I'm thinking is, because since the most patient, 80% of them are actually can be recovered from recovered can recover from SARS-CoV-2. due to the own immune system. So our body should be able to cope up with this COVID-2 if we don't have compromise with immunity. Remember, those phase 2 patients are immunocompromised patient, aged patient, diabetic patient, high blood pressure patient, and cardiovascular complication patient. These patients are actually having a certain percentage, a certain what you call level of immunosuppression or immunocompromise. So these patients are actually will lead to that phase 2 and failure of the management cause them to mortality. So
Hello,
I
sir.
So further, so further, do
Hello,
you
sir.
think that the virus is going to attack the central nervous system also? Because it's been seen attacking very vigorously towards the other sides of the body.
uh, no, remember the virus needs an entering point. The entering point for the virus is ACE2. In our body, which cell are actually express ACE2? Only type 2 alveolar cell expressing ACE2. If the nervous system cell expressing ACE2, yes, there is higher chances for infection, but we have no idea. And one more thing, is there any other way that SARS-CoV can enter the cell beside ACE2? We don't have any study yet. So the how do I say, the phenomenon here is quite broad and open. So we cannot give a conclusive answer. But based on existing information and the knowledge, those the virus enter into the virus can interact with the cell that express ACE2 receptor.
Sir. Hello, sir.
I
Hello, I am Rikshita from Anand Pharmacy College, Anand. Can I ask you something?
sure.
Uh, as we know that this COVID-19 binds with the ACE2 receptors. So, can ACE inhibitor work for the treatment for the same?
But see, if see, see, ACE2 also will have other physiological function like a CD4, right? No,
Yeah.
see, in HIV, you cannot what you call do prophylaxis by inhibiting CD4 because by inhibiting CD4, actually you're killing or you are deactivating the CD4 cell, which is a which is what you call necessarily needed for an immune response. Same thing here as well. ACE2 as well have other function by making them inactive using prophylaxis, using an inhibitory antibody. If anyone asking any questions,
So if there are not any questions, if anybody in the panel or anybody attending wants to ask some question, I think this is the right time to do it because I think we would be closing the session soon. That's why. Okay, I think that nobody has a question now. Vikram, would you proceed for the closing of the session, please?
Yeah, one more information for all the attendees. The link for webinar the assessment is opf.org.in/webinar. Please kindly note all the attendees link for the webinar assessment because your certificate is subjected to webinar assessment. Without your assessment, we not provide the certificate to attendees. So thank you very much, Dr. Rajesh Ramasamy, for your valuable presentation on immune response and COVID-19. It was, I think, it will be helpful for all the attendees who attend the session from across the globe. Thank you very much, sir.
thank you so
I would
much.
request, yeah, I would request sir to just leave his mail over the chat box so that anybody wants to have a query over the mail or forgot something, they can contact you by the mail.
Thank you so much for the Vikram, and also thank you so much Govin, and also the other panelists to for facilitating that webinar. And I wish all the best all the participants. But remember, always I wanted to reiterate, this is based on our previous experience of the SARS-CoV and MERS-CoV, and the new knowledge are actually bombasting that scientific field. Try to read the latest article and try to what you call assimilate, that will give you a better understanding of that the immune response towards the COVID-19. With that, I end my talk, and thank you for listening my talk. Thank you and
Thank
all
you
the
so much.
best.
Thank you.
Thank you everyone for the listening this webinar carefully. The webinar assessment link is sent it to your chat box. This is open only for till 7 p.m. After till 7 p.m., this link automatically regenerated and this link will be controlled.
Vikram,
Yes, sir.
sorry, I forgot to include that link which you have given to me early in my lecture notes.
Okay, no issue, sir. Not an issue.
I completely forgot about
Oh,
that.
yeah, okay, no issue. Thank you, sir.
Okay.
No
So,
problem. No problem.
so can I leave that? Can I leave now?
Yeah, sure.
Okay.
Your
Thank
call,
you.
sir. If you want to, your call, sir. If you want to stay with us for some talk, you can. There is no problem.
No, I have to go and cook now.
I agree to that.
All right, see you guys. Bye.